Hello community, I'm trying to rebuild the new OpenAI O3 model for my own 7B open source model, and I want to understand the mechanism of O3 because I think it is amazing. In my last video we looked at dependencies of the supervised fine-tuning to the inference time reasoning and also how here our reinforcement learning methodology influence here our reasoning capabilities for higher reasoning complexities, and now we continue. We have a new research paper by OpenAI that shines some light on the inner workings of O3 regarding here safety, and it is called deliberative alignment as an explicit rule learning methodology. So this means we move now from an example-based learning to a rule-based learning. You know, we do have limitation in the training phase, especially if we rely on implicit learning, because we need a huge labeled dataset. And the idea is, if we just have enough examples, then somehow the AI will understand the hidden pattern and come up, and suddenly we have a spark of intelligence. We know this is not happening, because the system is rather learning here only the pattern, but not really understanding here any rules that are based on the patterns. So therefore, we give now the model access to the specification of our training policy, of our safety policy, of our augmentation policy, and the model should now be able to retrieve all this information, but also reason over the text, let's say in the case of OpenAI, of the safety policy, instead of only memorizing here the correct response as given as an example. So here we go. Chain of thought is the simplest X of thought, if you want, here that we can use as a reasoning mechanism. Currently, we are at a forest of thought, and I have a video on this. But let's stay with the simplest case. Now we connect the prompt to the specific, let's say, safety policy, or you go with your summarization policy. And this chain of thought provides now a nice way for the model to explicitly identify the relevant safety rules and apply them to the input prompt. And this function now, and this is important, is a direct link between the prompt itself and the safety policies. I will show you an example that would make this a little bit clearer to you. But our main assumption is now simple. Now, we think now, or OpenAI showed us, that teaching now LLMs like O3 to explicitly reason over our policy, like the safety policy or any other policy that we have, via simplest way, chain of thought, is more effective than our old classical implicit pattern learning from labeled examples alone. So if we say, okay, we go with this, let's see where we can go with this. In my last video, I showed you here a reasoning methodology and this chain of thought for the supervised fine-tuning and the reinforcement learning for the synthetic feedback. Now it turns out those arrows are not the same training methodology. We apply different methodologies here, and now first step, let's understand why. Yeah, example-based, rule-based, beautiful. Chain of thought is now the reasoning mechanism, and we will now make explicit how a model arrives at its answer given here a particular training data set. So what we will do now is we will not watch here the LLM to generate a chain of thought, but we will define specific chain of thought as our training data for the LLM, and we will ask the LLM based on their training data now to argue over those training data, and you know that those rules define, of course, the policy. As I told you, with our two major errors here, we have now a two-stage training process. We have, interestingly now, a process supervision on the supervised fine-tuning, and we have an outcome supervision on the reinforcement learning method. And it is interesting to see why this different methodology was particularly targeted here, that the process optimization goes to the supervised fine-tuning, and the outcome optimization goes to the reinforcement learning. You remember, those are our two methodologies that are now a closer inspection, if I want to rebuild this myself in an open source model, I have to implement those policies and those methodologies differently. And it's all based, as I showed you in my last video, on this publication by DeepMind from November 2022, where they showed us already, hey, if you go with a process-based feedback or you go with an outcome-based feedback, the performance of your model changes significantly. And if you want, now we make use here of the final insights here by Google from end of 2022. Here's the complete overview in a formal logical way. Our two-stage training process 403 on the new safety protocol. This is the case we're going to look at, and then we use this idea and we will transplant this idea to any other further cases. So we start here with, for safety specification, S represents here a set of safety policies where each policy S is a set of rules. So S can be a text string representing safety policies. Then we have P. P represents the user prompt, and we have our classical chain of thought. C represents the chain of thought, which is a series of intermediate reasoning steps. So C, if you want, is a function here of our prompt, and S. And then we have an output, of course. O for output represents the final output, and this should be a function of G of C. And then with our new alignment goal, we should learn the mappings here, the function F on the supervised fine-tuning and this function G on the reinforcement learning, two different optimization procedures, such that in total, O, the output, is a safe response derived from using P using S. And now to the detailed goals. Our supervised fine-tuning goal is to optimize the parameters of the model to produce an accurate C for any given P and S. And our reinforcement goal is to optimize the parameter of the model to produce an accurate output O, which fulfills safety criteria given any C. If you're more into formal logic, easy. This is all we're going to do. But I have to code this to my system. So we have this two-stage training process. Let's focus here on the first part, the process supervision. So we will go down into the process itself and we optimize the process for our supervised fine-tuning. And I show you here the system prompt here for the LLM for the data generation, because at first we have to generate now this particular training data set for the supervised fine-tuning. So let's start. We tell the system always, you are a helpful AI assistant. Yes, your task is to analyze user prompt in the context of specified safety policies and provide responses that adhere to those policies. Later you can exchange this with argumentation policies, with, causal reasoning policies, whatever you want that the system is doing in your way of argumentation, in your way of referencing to, literature or whatever. So whatever you define as an abstract policy, you can imprint what you want on the system now with this particular methodology. So you will analyze the prompt, carefully examine the user prompt, we tell the AI, identify the relevant policies, determine if any of the provided safety policies are relevant to the user prompt, reason over this policy, this is new, no? If a policy is relevant, explain how this prompt by the user relates to the policy that we provided the system for the safety policies, noting if it violates, if it complies with, or it needs safe completion as per policy. Then you cite the policy. We want to have a transparent AI system. I want really to see that if I have given, 17 steps, I want to see here, this is step number 12. Cite the policy. If a particular policy set is used, explicitly mention the exact wording of the policy. Therefore, I can see if the AI is really using the complete set of policies I give to it and provide a response. And here's the safety policy. This is just a short demo for you. Here's a safety policy you should adhere to in all contexts. Do not engage in personal attacks or make derogative comments about other user. Now consider the following user prompt and generate your chain of thought reasoning and your final response. So to generate the data, I need a system prompt and a user prompt. So the user prompt is simple. Hey, I think user X ideas are just plain stupid. And now the response by the LLM given our system prompt is now, it builds here a raw first step chain of thought structure. So for the data generation, we get now this piece of data that we need for the data generation, for the supervised fine-tuning. So I get user prompt includes the statement, yes, 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 according to the policy, do not engage in personal attacks. It violates this policy and I should not comply with the request. Therefore, my output tells me the LLM, I'm sorry, I cannot provide a response to this. So here I have it now. I have now this new piece of data. I was looking for the chain of thought for my training data, where, according to my instruction, the system cites now the explicit policy I provided it with, and it says, yes, complies, not complies, or whatsoever. So you see the data generation is here absolutely 100% synthetic. Now, all those chain of thought, they're built at 1,000, 10,000s, but the quality is different. So what we need is a filtering process. And you have a reward model, or you have an AI judge, or whatever you have. Let's go with the classical, like OpenAI does, the reward model. So this is now the quality filtering prompt here given to the reward model in my case. Following is a conversation between a user and an assistant, and here we have now the output, prompt, chain of thought, answer. And I tell now the reward model, hey, your goal is now to rate the assistant final response to the user for correctness, helpfulness, compliance, as well as the quality of the chain of thought. This is important. So tell now the reward model, hey, analyze this and tell me if this is the best chain of thought possible. And that is how your rating should be based on response compliance with the overall, let's say, OpenAI policies. You can list here the policies, you have optional policies, and the final instruction is judge the response according to the policy. So what we get from the reward model, an output, and this is simply a score, or you can say agree or disagree, or high quality or low quality for our data filtering during the data preparation for the SFT. So this synthetic filtering allows now for a created dataset of prompt, chain of thought output tuples, ensuring that only higher quality data are now integrated in our training data for SFT. The high quality, non-human generated, supervised fine-tuning training dataset for here our alignment phase is now in the form of prompt, chain of thought, output, a tuple, and here you have one examples that passed here the high quality check benchmark, the threshold, prompt, chain of thought, output. This chain of thought is real simple. You see it's just one step. But you can build systems where you have 2 steps, 3 steps, 5 steps. So it's really how complex you build your chain of thought, or you would tell the LLM to build your chain of thought. Great. Let's do the summary for the first stage, for the supervised fine-tuning stage, for the O3 model. So the model is trained on synthetic data only, comprising a particular structure of prompt, chain of thought, output. This is our training data. Chain of thoughts explicitly reference now the safety policies. They quote the safety policy. It's now an inherent part of the training data, and outline here a reasoning step or multiple reasoning step required to address the prompt. Simple example. So what we have instilled now our structured reasoning path of our safety policy into the model, into the training data set. But in a way that is much denser. We don't provide simple input-output data sets, but we provide here with this triplet prompt, chain of thought, output here, a much more structured reasoning pathway. And those pathways have a certain complexity. And we will encounter another threshold in about 5 minutes. But let's first come to the second stage of a 2-stage training process for O3 here under safety. And now we are here in the reinforcement learning. And now we do something similar to outcome supervision. And we say with outcome supervision, the optimization process is not focusing on how to do this. This is done here. But now we just see if the outcome is correct or incorrect. Simple. So this stage now refines the model's safety reasoning and optimizes here the quality of the chain of thought by focusing on the final output. It's not so much that it optimizes here the chain of thought steps itself, it is really focusing on the output and the reward. Now, reinforcement learning we have provided by the system is now a reward signal for evaluating here the quality and improving here the quality for our reasoning. But what is important here, this reinforcement learning phase employs here a particular judge, an AI model, a reward model, whatever you have. Now we have the second time maybe an external system that is really evaluating our quality for the training data set. And this is a strong dependence here on this reward model, on this AI as a judge model or whatever you like, to assess here the chain of thought reasoning, which provides us the final output. And the final output is now exactly what we want to evaluate. Specific criteria, correctness, policy adherence, coherence, and effectiveness. Is it reasoned correctly? Does the reasoning process align with the predefined policies? Is the reasoning policy clearly defined? And so on. But again, this is a critical dependency on our judge, on our AI model, on our reward model, because if the reward model is not better than the model that we want to create the training data for, we are stuck at a particular level. This reward prompt for the reward model that I use here is now in the reinforcement learning stage here. So this prompt is given here to the reward model I use to generate here the reward signal. Note that the safety specification are provided explicitly here in the reward model. So my reward model has all my instruction set given here, or OpenAI's here safety instruction given here. And note that a particular chain of thought reasoning process is not provided to the reinforcement model, because I don't want that it goes again and characterizes here the reasoning complexity correctness. I just want here, is it the good answer or a bad answer? So I say here in the reward prompt, the following is a conversation I use and an assistant. Prompt, extracted answer. So you see, missing is here the chain of thought. And I tell here the reward model, hey, your goal is to rate the assistant final response to the user for correctness, helpfulness, compliance, and whatever else you want to add. Your rating should be based on response compliance with, OpenAI tells us here, with the OpenAI policy of this simple sentence. You have your list of whatever policies you have optional policies, and the final instruction to the reward model is now judge the assistant response according to the policy, safety policy, augmentation policy, whatever. And then you get a result back from the reward model. Let's say if the scale is between 1 and 5, 4. So this is now, as you can see here, you just get a reward model, a reward signal back from the reward model. And then you use this here for, and you remember, you can't go with DPO alignment because we need this reward model here. So it's used now to tune to have a reinforcement learning alignment via the old classical PPO, the proximal policy optimization by OpenAI, further optimizing its ability to generate policy compliant outputs. So you see, this is it. So if you go now for the summary for the second step here, the reinforcement learning part for the O3DA, we do have this either external or internal judge model. This reward model evaluates here the outputs by the model for correctness, policy adherence, coherence, whatever else you want. The explicit chain of thought is not given to the reward model here. This is to ensure that the model generates just the correct output irrespective of its reasoning. Because if we get another output by a reasoning path that is maybe unknown to the reward model, I just want that the reward model tells me, hey, this is the correct output, and there's a new reasoning, and I don't want that the reward model judges now if the reasoning process itself is correct or not, but maybe this reasoning process is better than what the reward model knows. And, example, reward model rewards a chain of thought that correctly reference specific policy guideline to justify refusal while penalizing responses that omit essential policy checks. The outcome is simple. It refines and enables here a policy-aligned output that is correct in any case, that is robust and nuanced and whatever you have here in the reinforcement learning. And the key difference is here now that unlike the supervised fine-tuning, where we wanted here the model to learn how to create a chain of thought that has a particular reasoning pathway over the specifications in the policy given, now in this reinforcement learning stage, we focus here on the initial output only. So the explicit chain of thought from the supervised fine-tuning is hidden, and we want to have here this SFT plus the reinforcement learning. And we know from empirical data from Google DeepMind that if we set up this process, they achieve a higher performance than in any other combination. If this is still true for an O3, we have to evaluate on the available O3 model itself later on. Interestingly, that OpenAI tells us in the technical paper, while the supervised fine-tuning portion of this, what I just showed you, was used for all serious models, so O1, O3 completely, the particular reward signal for the reinforcement learning was added for the training of the O1 model and the O3 mini model. So there's still a secret about the O3 full version, but you know what? I'm already happy with an O3 mini procedure that works as great as O3 mini. So if I reflect now today on day 3 of having at first access to the O3 model, how can I build my own? If I want to train here my 7B open source LLM, I think I have to go through the same steps like OpenAI. I have my supervised fine-tuning, chain of thought training data set that I have to define. I have to go through the reinforcement learning based on the chain of thought argumentation we just had a look at. And this combination that is then an optimized combination will be my test time reasoning procedure that is also based then on chain of thought. So you see, great. But then if I run the first trials, I find some problems. Let's have a look at this. I see that the complexity of the reasoning of my new system here is limited to the complexity of the chain of thought training dataset. Because remember, this training dataset was synthetically generated here by an LLM, and I have it simple. I have here simply the access to a better model, to the O1 model, because I have here only a 7B model in my open source case. So I hope that O1 is so excellent that the training dataset is just amazing for the 7B model to have these training datasets. However, I see that the quality that the O1 provides is limited to up to a certain complexity level. That's it. And then that's it. We reach a plateau. And I said, okay. And I also see that the evaluation of the reasoning is limited. You know, the second time we have this judge AI or whatever we call this, or the identical reward model, if you want to go with this configuration, is also limited by the correctness of AI as a judge on the correctness. Now here I can help myself, no? Because OpenAI API 01, I have access to a Python program, Prolog, whatever. I can just convert certain problems into Python code or the Prolog or whatever. And I can simply run then a Python program for the mathematical correctness. I get the real value back. So I just have to code all of this. And I get here a mathematical evaluation of my topic. And with this mathematical evaluation, I have a second order correctness test if O1 was correct. So O1 codes this, find out in code that it is either correct or not. And I have here, if you want here, a further correctness cycle. I do not just rely on the inherent correctness of O1, but O1 validates its own reasoning here for the evaluation with Python Prolog whatsoever. And you might say, great, but this is also a limiting factor because there is still here an open question mark. And what I find out in the very first trial, I'm just 3 days in, but this AI config is not self-learning higher complexities. And this is a problem because AI should be able to this spark of intelligence, This is what I want from a system. Because if all my chain of thought training data, they have a specific form, a specific shape, and a specific inherent complexity. And if the system is only able to come up to this training data set complexity, and the system is not able to go at least one step further, then I just have the complexity of my training data set. This is all the AI can do. And this is disappointing for me, because I want to go this step further. I want to have a self-learning AI that is able to go to the next level of complexity. I want the AI is able to combine somehow thousands, millions, trillions of chain of thought ideas and come up with a better reasoning structure. But according to day 3, it's not happening in my model. So I looked here at this publication. Maybe you're here helpful. Maybe you have some insight into this. The latest reinforcement learning. This is from Berkeley and ETH Zurich. Boosting exploration and reinforcement learning through information gain maximization here. You see mid of December 2024. And they combine here the Boltzmann exploration with the maximization of the value function, with that of the entropy over the state, the reward and the actions. And I just started to think about this and how to implement this. So this is here an open problem for me. I'm working on this right now, today. But I also thought, hey, this is somehow related to this video where Meta showed us that it went from a pure language model to a concept model. And if you've seen this video of mine, this concept is exactly this level of abstraction. It is also not giving here from the language here the single elements of our language, but what is the underlying principal concept. And it is feeding the concept into the model and into the training phase. So you see, OpenAI is doing this here. Meta is already doing this 2 weeks ago. But I think there is this trend now happening where everybody is trying to come up and train on higher complexity levels. And I even went there because I thought, hey, is a diffusion-based large concept model maybe the solution? Because if the training data set in an LLM is the limiting factor, maybe the diffusion process itself is able to come up with higher complexity reasoning patterns. But as I told you, I'm still here in day 1 of trying to understand how to implement this. But the question for you is, can a diffusion model generate a novel, higher complexity reasoning chain, a chain of thought, or higher complexity patterns in general than a pure large language model that is not diffusion based? Is diffusion here our additional way out to go to higher complexities? I don't know today. And of course, self-refine, and this is also what OpenAI referenced here, in their experiment, how they were trying to do this on O3, and they tell us they also tested here self-refine, where the reasoning occurs through a structured few-shot prompting, and you remember here, May 2023. This self-refine, this iterative refinement with the self-feedback here by Carnegie Mellon, NVIDIA, and Google Brain, you see that almost everybody is fighting with this idea. We are limited by the complexity of our training data set. If I want to have a better, more intelligent way to argue, more clever way to find causal reasoning pattern, but we can't. The AI is not doing this. We are limited in our black box, in our complexity given by the training data set. And this is something that I think, we have to overcome this limitation. However, please note what we achieved. We achieved a scalable synthetic data generation, which is amazing. We achieved a generalization that is working with out-of-distribution scenarios because we are not giving any more single examples where the system is learning of this, but we are giving, if you want, the reasoning pathways we imprint in the decision-making, and therefore we are not so sensitive to OOD. Plus, we have now an adaptability in the system to dynamic policies. All beautiful, all great, all amazing steps forward, but the one single step is missing, you know? And if OpenAI writes here, the impact now on the test time compute of O3, then, for example, here DA leverages the test time compute for the reasoning over policies at inference time, that it is now able to dynamically adapting to complex scenarios. And as I've shown you here in this video, where O3 failed on this test, I don't think that O3 is really dynamically adapting on complex scenarios. Because I've showed you in this example, if we have this in context learning on a visual data, and the system is not able to understand if it has here on the periphery here, the blue indicator to construct here the blue lines or blue rays or whatever, just if I add another line, just plus one line. If this level of complexity to add one line makes that the system is not able to solve this problem anymore, I don't think that O3 is dynamically adapting to more complex scenarios. And this is not okay. I want that my AI system can do this. So, you see, in biology, we have exactly this. Think about a DNA strand. We have tiny, tiny little complex single molecules. But the way we built them, nature discovered a building pattern. We found here this amazing structure that is really able to spark here intelligence. But I think with AI, we are still missing this particular way of building complexities. Okay, I think this is it for today. You are really at the very moment where I do build here my own O3 model on a simple 7B model and open source model, but I'm trying to understand how to implement these O3 ideas into the supervised fine-tuning, how to build the supervised fine-tuning dataset, how to set up the process of the reinforcement learning that it is compatible here with the chain of thought reasoning process, and then apply this new trained optimization here on the test time, on the inference compute that is also based, giving here a chain of thought here in the final answer. And this is here where we have those famous 13 minutes that O3 might take to think about a single query by the user. But you know what? If you subscribe, hey, maybe you are interested if I continue here with my with my task, with my exercise, because I think it is fascinating if we would understand here the theory behind it. And it is a simple implementation. And for code, you can use whatever you like from Cursor or Bolt or whatever. Go with it. We just need the idea. And the implementation is more or less a standard implementation. If we know how to do it, we can code it. So I hope this video was also a little bit of interest to you. You found maybe some new ideas. And it would be great to see you in my next video.